Okay, so what did we do on Tuesday? So last class was a very sort of big day. Oh yeah, so hold on, someone has a question. I will take time to answer this. It's a private one. By the way, the question had to do with the final. The final will be a take-home test, similar to the midterm. So if you're curious how we're going to do that, it'll be something that I post to, I'll post it to Canvas, and you'll have, I'll fix some amount of time that I want to give you, whether it's a day or 6 hours or 4 days or whatever, and then you'll just have to submit it to me somehow, some way. Whether you put it in an envelope and mail it now, or you upload, email, whatever. We'll figure that out when the time comes. All right. Okay, so what did we do last class? Last class was a big day for us. We talked about a very important concept. So that was the idea of a power series. So motivated by Taylor polynomials, what we discussed on Tuesday was power series. I guess I should write this. And why was it motivated? Well, we've done a fair amount with these Taylor polynomials, and we kept asking ourselves, what if we let the order of the Taylor polynomial keep getting larger, say, n the 8th degree, or the 10th, or the 50th, or the 100th, or the 1000th? What happens? And what that suggests is that maybe we can actually somehow make sense of a polynomial that has infinite degree, if you will. And so that sort of suggests studying something that's a power series. So let's remind ourselves of what a power series looks like. It's anything that looks like this. So here's the general case. It's scariness. So when you plug in k equals 0, you get c sub 0, and then when you plug k equals 1, you get x minus a to the power 1. And then when you plug in k equals 2, you get this. And we say that this guy is centered at A. That's the general case. Boom, 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 boom. So this creature is centered at A. And then we stated results for the simpler looking guy, which is just this guy. And so this is a number plus a number times x plus a number times x squared plus a number times x to the third. And this goes on forever. And in this particular one, we would say is centered at 0. So if you look at either one of these, there's a clear pattern. And so we stated a very generic sort of statement. You know, the way you read this stuff in the books is in the books they have these theorems, because that's what they are, they're theorems. And they say, here's all the cool things we can do with power series. I just, you know, that's to me, in my opinion, is overwhelming to students in your situation. So I thought the best way to proceed is to sort of show you all these manipulations and tell you that they're true, they're legal, they're not illogical. And the reason that they're legal is that there's this deep theory that says they're legal, provided that we're only saying these things are true for values of x inside the radius of convergence. So here's what we stated. We stated that we can, quote unquote, manipulate power series to obtain new ones, provided we understand convergence depends on the interval of convergence. So let's just remind ourselves of some of these things that we can do. So what we did, and this is a very standard thing, and we're going to ask you to do it as well, is you start with a known power series. And right now we don't really know many. We do know one, and we generated a bunch of new ones from just knowing one. So starting with the power series that comes from the geometric series, so starting with this, and we know that this guy is only true provided that x lives between -1 and 1. We can obtain new power series. So we showed a few of them. So for example, last class, we integrated the above. And what is the above? It's an identity. And what it did is it gave us information about the log. We found that negative the natural log of the absolute value of 1 minus x has a power series representation. And it looked like this. And we did some stuff to help convince you that this was indeed a true thing. Again, provided, let's be very clear that if x was between -1 and 1, this is true. We even went to Desmos and we graphed a bunch of stuff and we said, hey, look at this. The graph is suggesting that the math is in fact correct. And so we're excited about that. Does anybody have a question about that? We're going to do another example right now, a very, very important one. Okay, questions? All right, so let's play another game. So here's an important example. So start with this. So let's start with our base power series. That's this guy. So you guys need to know this like the back of your head, as the saying goes. Start with this creature. And what I'd like to do is I'd like to get information on a particular function. So somewhere in the back of my mind, I want to know about the arctan. And so what I'm going to do is I want to use some deductive reasoning, some investigative reasoning, or whatever you want to call it. I want to figure out something with the arctan, and I have to figure out a way. Is it possible for me to manipulate this guy that I have written down so that I can get information about the arctan or the inverse tangent? And the reason I'm even thinking that there's a chance is because one of the things I know is that the inverse tangent has a derivative that is not exactly what I see here, but it's similar. And so I ask myself, how might I be able to get information? So what I'm going to do is I'm going to replace x with negative y squared. So when I do that, I end up getting this. I get 1 over 1 plus y squared. And then that's going to be equal to 1. And instead of x, it's going to be minus y squared. Oh, my penmanship today, as always, is suspect. So this is minus y squared, and then when you square it, you get plus y to the 4th, minus y to the 6th, plus y to the 8th, minus y to the 10th, and then this goes forever and ever and ever. Now, what values of y is this true? Well, this is only true when negative 1 is less than negative y squared is less than 1. Now, if I think about this inequality, I will recognize that this is the same thing as me saying that negative 1 is less than y is less than 1. You can either reason that out in your head or you can do the algebra, but it is true. Now, what would make me want to do this? Okay, well, as I said before, and we can even give this a name because it's worth you guys knowing this. This example is important. What we're doing is we're deriving a series for the arctan. And so, being that that's my goal, I am trying to build something so that I can manipulate it to look like an arctan or an inverse tan. And so, if you have that in your mind, you'll say, okay, now I see what he's doing. Because if you have any knowledge about the inverse tangent, aka the arctan, you know that its derivative is 1 over 1 plus input squared. Which tells me if I take that equation with the y's in it and I integrate it, I am going to obtain an arctan. So what we do next is integrate. So if we integrate, I had 1 over 1 plus y squared dy. So what do we have? Well, now we're going to integrate both sides. So on this side, we had 1 minus y squared plus y to the 4th minus y to the 6th. And you have this. And this implies that the arctan of y is equal to, well, now take the integral. This becomes y minus 1/3 y cubed plus 1/5 y to the 5th minus 1/7 y to the 7th plus dot, dot, dot. And then, of course, once that thing ends, there's this plus c, if you will, at the end. Now, we have to use a basic fact. Since the inverse tangent, or the arctan of 0 equals 0, we obtain by substitution that c has to be 0. And if that's the case, what we just were able to deduce is the following. We know that the arctan, and I'll write it back in terms of x because why not? The arctan of x is equal to x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th. And that goes on forever and ever. Now, of course, this is only valid when x is between -1 and 1. But nonetheless, it is valid in that particular domain. Does anybody have a question about this? Okay, so let's do the obvious fun thing to do in these scenarios, and that is go to Desmos.
Why did you plug in 0 for arctan of 0?
Why?
Yeah.
I wanted to know what C was. And so I know that if I replace arctan with 0, I know what the arctan of 0 is. It's 0. And so that would kill both sides of the equation. So it's me using what you'd call deductive reasoning. That makes sense? Or deductive reasoning is actually a poor way of saying it. It's me using an educated guess or something that I know to be true. Because maybe that constant was 6 or maybe it was 9. But how do I get anything out of it? Well, I say if I choose 0, then I get information about C because that makes everything disappear. Does that make sense?
Yeah.
You sure?
Yeah.
All right, cool. All right, so what I'm going to do now is I'm going to send you us to Desmos. So hopefully you all see Desmos, and now we're going to graph it. Who is in my house? Oh my God, George the Barber's here. So if I graph y equals the arctan of x, I get this red curve. And what I want to do now is I want to start graphing some of that polynomial, x minus a third. Oh my God, someone's at my door. Hold on a second. Plus 1/5 x to the 5th. And even if you'll see if I just graph the first 3 terms, that blue is right on top of the red. Give me 1 second, gang. I got someone at my door. Sorry about that. That gave you time to catch up at least. That was my barber. He stopped at my house to see if I wanted an illegal haircut in the quarantine. Can you believe that?
Legal haircut.
This is the life I live. I'll tell you what. All right, legends. So anyhow, we're back to this beautiful picture. Does anybody have a question about this picture that you see on Desmos? Again, you can already see with just 3 terms, I'm pretty accurate. Look at that. I mean, between -1 and 1 at least. So if you move, obviously, if I add another term, 1/7, x to the 7th, it increases its accuracy a little bit. So, or, well, maybe not. I don't want to get too illegal here. Does anybody have a question about this?
So that means it only will go through the range like 1 to 1?
Well, not the range, but it's only going to really work between -1 and 1. And actually, the more terms I add, the steeper the outs of the blue curve are going to get. So it's not going to work outside of -1 to 1.
Okay.
Now, you might say, well, I want to know something about the arctan on another interval. Well, that's fine, because you can just take your power series and move it left or right. That's all you have to do. How do you move it left or right? It's pretty straightforward. You just you learned how to do that in previous classes. So you could just get your power series centered at a different number. We'll show you how to do that probably today, if you're interested. Does anybody have any questions about this? All right, now here's a cool fact that we can get back to. And so we're kind of sort of, well, okay, we'll skip that. We'll leave that in case it's a project. We don't want to steal too much fun from you guys. Okay, back to the whiteboard. So anyhow, now we've now written the arctan as a power series. So that's pretty good. Does anybody have any questions about this? I mean, think about it. You could spend the rest of your life taking the geometric series and deriving new series from the geometric series. You can, excuse me, I'm getting confused. It's like I'm having a senior moment. If you start with the geometric series, you can derive infinitely many new series. So it's pretty sweet. Does anybody have any questions about that? Comments, concerns? Okay. So, cool. We now know we can work with power series and we can do lots of stuff. But don't forget, and actually, I believe we talked about this a few times on Tuesday. I'm not saying anything about what happens at 1 or -1. you would have to look at those series in their own their own scenario. So for example, the arctan of 1 might not necessarily equal 1 minus a third plus a fifth minus a seventh. You would have to check that separately. Just as the arctan of -1 might not equal -1, etc. Now, the graph we're doing suggests it will, but we don't know that. That takes more analysis. It requires more hard work. Okay. Does anybody have a question about this?
Yeah, can you stay there for just a second?
Can I stay here? I can stay wherever, dude. I am not going anywhere. Let me know when you're ready.
All right, I'm good. Thank you.
Good? Yes, sir. Okay, so power series are very nice. And what we showed is starting with one power series, we can generate new ones. And so that's one way to think of the problem. But another more practical way would be, given a function, how do we find, does it have a power series? So let's write this down more precisely. So we've now shown that what we can do is so we can determine lots of power series from this creature. I'll write it again because you can't know this thing enough. So we've now shown that we can determine lots of power series from this. And most importantly, and they represent functions on the interval of convergence. Some of these are known functions. I mean, hey, we just figured something out for arctan. We figured something out for log. We can manipulate and figure things out for lots of different rational functions. So now we want to ask the reverse question. And that goes the following. Does this mean every function has, okay, so let me write this in a sort of an illegal way, but I think it's clear for what we're trying to get you to appreciate. So does this mean every function can be written, whatever that means, as a power series? So I want us to be very careful with how we're using the language here. I'm putting the word written in quotations because what does that really mean? If you think about the previous examples, or if you look at this power series that I have on at the top of this page for the geometric series, that power series, what we're saying is 1 over 1 minus x can be written as a power series, provided, of course, and let's not fail to put that very important fact in, that -1 is less than x is less than 1. So what we're saying is 1 over 1 minus x is a perfectly valid function at every point except 1. However, we're saying that when x is between -1 and 1, we can express it as a power series. And so what we'd like to know is, given a function, can we find a power series that it's quote unquote equal to? Okay. So let's state that more precisely. Well, I guess instead of stating it first, let's make a definition. So we already have a candidate for this, and if you think about it, you'll realize, oh yeah, we do. So let me state it a little carefully. If I give you a function and I want to ask if it can have a power series, if it's equal to 1 or can be written 1. Well, we already saw that if we find Taylor polynomials, those guys are good at approximating. So we would expect that if a function's going to have a Taylor, or excuse me, I'm speaking out of place here. If a function is going to have a power series that it's equal to, or we can write it as, then it would just have to be an extension of the Taylor polynomials. So this suggests the following definition. I mean, we might as well recognize that if anything's going to work, it would have to be writing a Taylor polynomial as a series. And so that suggests the following. Given f of x, or given f, we call f of a plus f prime evaluated at a times x minus a plus f double prime evaluated at a over 2 factorial times x minus a squared. We call this guy the Taylor series of f centered at a. Now let's be very clear. It's possible that this thing doesn't exist. If a function doesn't have derivatives, you can't compute this. So let's put that little caveat in. So given f, we call this series the Taylor series. So this is just a Taylor polynomial that doesn't end. It goes on forever. Anybody have a question about this? So,
Hey, can you go back?
sure.
All right.
Good. All right. Anybody else?
No.
All right. Okay, so If A is equal to 0, we give it another name. We call it the Maclaurin series, named after the mathematician Colin Maclaurin.
We just can't call him the McLaren series.
Well, you could if you'd like, but the way you pronounce him is the Maclaurin. Maclaurin, he was an Irishman. So if A is 0, you have that. So this just becomes f of 0 plus f prime evaluated at 0 times x plus the second derivative evaluated at 0 over 2 factorial times x squared, and then the third derivative evaluated at 0 over 3 factorial x cubed, and then this creature goes on and on and on. And so once we define a series, anytime you come across a series, the very first thing that should happen is you ask yourself, does it converge? And then with these creatures, there's even a second question you'd be interested in. Not only does this thing converge, but does it converge to f of 0? Number one, does this thing converge? More specifically, for what x? And then lastly, does it converge to f of x? So these are some deeper questions. You might have to think about, okay, what does he mean? Again, we're starting to get into some higher math, and you're going to say, wasn't this already high? Oh, this is calculus. This is, it's high for most people on the planet who don't have to take it. But for those of us who take science courses and engineering courses, this is the fundamental math that is necessary, calculus. So we're starting to get into some very important ideas that are used in many, many areas of physics, of engineering, of applied chemistries, and applied biology. And you hear all this stuff now about epidemiology because of the virus. I mean, you name it out there, there's people who use this stuff, Taylor polynomials, Taylor series, to study and try to answer tough questions. So we've already computed a bunch of these. We know some of these. And watch how careful I am when I write this, because it's important you see that. So let's look at some Maclaurin series we know. E to the x, what's its series? It is 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, ... Let's choose a different color. Colors are fun. Pink. We know the creature for the sine of x. We know this is x minus 1/3 x cubed. Excuse me, 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. We know that. And then we know for the cosine. And if you remember, I said these guys are quite easy to not forget because of the pattern that we have. So one of the things I really want to emphasize to you is that I did not write an equal sign. So note, I ain't saying, let's talk very appropriate. I ain't saying they're equal. But of course, you might suspect that they are. I just didn't say it yet. Because it's not always going to be the case. So what I mean by that is if you refer to the previous whiteboard where I said there's these two questions we're interested in, it is possible for a Taylor series to converge. It is possible for it to diverge. And it's also possible when it converges that it doesn't equal the function. Now, you might say that's impossible. Look at all these pictures you showed us. Well, there are examples where it doesn't, so maybe that's a project for someone. People like extra credit, I don't know. Does anybody have a question? Okay, good. All right. Now, the good thing about this is we're not really creating anything new. We're just telling you that what you learned how to compute before, the Taylor polynomials, that these guys, if you just put a plus and an ellipse after, you now have a Taylor series. And so the question you want to ask is, does it converge? Okay, so if there's no comments or questions, we will move forward. See anything on the chat board? So, Jeff, I think you were the one who initiated this conversation maybe 2 classes ago when we talked about this, how good are the approximations? And it turns out that for some very nice functions, the approximation can be as good as you want it, as I suggested. And I also suggested that that the study of error and the analysis of error, and frankly, the answer to those questions that I just posed is really, it's really meant for a class that's a little bit beyond this. You know, we don't want to get into the technical details of proofs because it relies on some more deeper ideas. But it is worth pointing out that there is some big theorem. It says the following. So suppose this limit exists. So suppose the limit as n goes to infinity of this creature. So suppose this equals 0 for some c, or really, yeah, I guess we could say it that way. So if C is some number between sort of, imagine what we have here. X is some number. So I guess we can just kill, instead of writing it down in a scary, we could just be very generic with this. It's not wrong. So if C is any number between, say, X and A, and this limit equals 0, then the Taylor series for F converges to F. On an open interval containing X, or excuse me, not X, A. So I'm writing this down. We're not going to prove it, but it's actually, you could prove it in this class. It's sort of sketch it, I guess, is a better way of saying it. And this is by no means an easy limit to sort of calculate, because in order to calculate this, you would have to have some formula for the nth derivative of a function. By the way, this let me clean this up a little bit. So if you want to think about what this theorem is good for, it's good for answering those questions that we talked about. So maybe I will put that up here. This is the big theorem, and it tells us when the Taylor series, which looks like this, when we can actually say it's equal to f of x. Whew. Okay, so are you going to need to use this theorem? No, but I felt the need to write it down, and so that maybe you can think about this. By the way, this is the term that helps you measure that error. We often call this the remainder term. So if you're interested in the error of Taylor polynomials, this is the kind of the guy that gives that to you. There's a thing called Taylor's theorem out there that you could study, and this is connected with it. But we're not going to get into that. So what do we care about? What we care about is what's important in this class is we care about the following. So if we apply this theorem to e to the x sine of x, e to the x, and etc., we can deduce the following. So we can deduce, for example, that e to the x is in fact equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed. So notice now I'm writing that equal sign. Because if I take the nth derivative of e and compute that limit, it's going to be 0. And then the same thing is going to be true for sine. We can write sine as x minus 1 over 3 factorial. And the nice thing about these two, for example, this is true for all x. And this is true for all x. And you can list, what's that?
Are we applying the standard e to the x sine of x, then e to the x again? Or is that like supposed to be a different?
What do you mean e to the x again? Oh, yeah. I don't know why I wrote that. I see what you're saying. Yeah. Thanks, dude. That can be, sorry about that. Yeah, I wrote e to the x twice because it's O'Grady. Such a cosine. And what do I mean by et cetera? Well, you can write one for cosine. And then we have all the other guys that we already deduced all have power series. So you can say we already know 1 over 1 minus x in the tangent. And so we can now write cosine as 1 minus honk, honk. So these guys, where some of those other ones were only true for certain values of x, these guys are going to be true for all x. And that's very, very nice to know. So what we're saying is that there's a very special type of power series out there. It's called a Taylor series. And it is extremely useful. And it's very easy to calculate in the sense there's a nice formula. Now that formula relies on the fact that you can compute derivatives. But if you can, then you're good to go. So there's some very cool things that you can think about with these series. I mean, look at e to the x, take its derivative. You get what you started with, which shouldn't surprise you because you already know the derivative of e is itself, right? Take the derivative of sine. What do you get?
Cosine.
Well, right, but I'm saying look at the power series. Take the derivative of the series. What's the derivative of x? 1. Look what's below, right? If you differentiate that, you get cosine. So there's all kinds of interesting things that start to piece together here. Does anybody have a question about this? So in many areas, look, so all the tools we have with power series, we can now put all this together. And you're going to start to see why Taylor series and power series in general are such an important tool in science and engineering, because they take complicated calculations and can reduce them to much simpler ones. So let's do that. So it's often useful to work with Taylor series when doing lots of things. Not just calculus, but math in general. So what do I mean by this? We can do things like we can use them when computing limits. derivatives, integrals, differential equations. They can often vary, I shouldn't say they can often vary. They often can take complicated computations and reduce them to simpler ones. Some of you will get to see this when you take certain classes in, say, computer science, if you do, where you might have to analyze algorithms and you want to know how many steps does an algorithm take to complete. So this is something that for, some of you won't get to enjoy any of this. I was just telling the Calc 3 class yesterday, one of the shames of the calculus sequence is that many students are forced to take them because of their major. And then they're really only used in a class or two, and then you kind of don't get to see what a lot of the other stuff is useful for, unless you take certain classes. So, I kind of feel bad that some of you won't get to see how useful some of this stuff is, whether it's in physics or engineering or biology or chemistry. But using Taylor series to help with calculations is one of the more important tools of math being used in certain areas. Let's do some examples of what I mean by that. Let's do one of each. Suppose we want to compute the following limit. So suppose we want to know, how about the limit as x goes to 0 of the sine of 5x over x. Now there's a few ways that you could evaluate this limit. You could absolutely take this limit. You could use, say, L'Hopital's rule if you wanted. However, many complicated limits require L'Hopital more than once or require some very unique tricks. This one is a simple limit, but it's a good illustration of how we can use power series. So what I'm going to do is I'm going to replace sine with its power series. So what's the power series of sine? We know what it is. It's x minus 1 over 3 factorial x cubed, but I'm going to replace that with, this becomes 5x minus 5x cubed over 3 factorial, and then it's plus 5x to the 5th over 5 factorial, and then it's minus, and then that goes do. And this is all over x. And then those big theorems about power series say, okay, I can treat these things just like normal polynomials. I can take that 1 over x and plug it into all the pieces. So this becomes, the limit as x goes to 0 of 5 minus 5 cubed x squared over 3 factorial plus 5 to the 5th x to the 4th over 5 factorial. And what you recognize is that every term from the second one on has an x in it, which means when you evaluate the limit, which is legal by our big theorems, you get 5 minus 0 plus 0 minus 0 plus 0 minus 0. So we conclude that the limit is nothing more than 5. Does anybody have a question about this?
How did you get the 5 minus 5 cubed x squared?
What's the series for sine?
No, the second.
Yeah, so right. So what do you plug in? What is it? So when the sine, you mean how do I get the square?
Yeah.
Oh, we'll take x and the x cubed. There's 3.
Oh, okay.
If I take x in, and that's how the 5 becomes a 4 as well.
Okay. Okay.
Does that make sense?
Yeah.
Let's do another one. So suppose we wanted to ask this limit, which we've studied a few times before. What's the limit as x goes to, say, infinity of x to the third e to the negative x? So this limit is the limit as x goes to infinity of x cubed. What's e to the x? Well, e to the x is 1 plus x plus blah, blah, blah. So this becomes 1 minus x plus x squared over 2 minus x. So when I plug negative x in for this, this becomes minus x cubed over 3 factorial. And then this is plus dot, dot, dot. So what do we end up having here? If I take the x and I multiply it through, I have the limit as x goes to infinity of x cubed minus x squared. Excuse me, x to the fourth, pardon me.
Shouldn't that be x squared over 2 factorial?
Yeah, but what's 2 factorial?
2.
Yeah.
Like,
Yeah, you
yeah.
could write that if you wanted, but
For simplicity.
trying to keep it somewhat not crazy here. So what happens here then when the 3 and the x squared, you get x to the fifth over 2, and then this is minus x to the sixth over 3 factorial. So right now, let's look at this, because this looks like we're going down a dead end. So it should be noted that you could compute this limit using L'Hopital's rule. And if you do that, what you're going to get is you're going to get that this limit is 0. But by what we're doing, does it look like it's going to be 0? So again, look at what we have here. We're trying to compute this limit here. It looks like we're getting worse than we're getting better. And so I want you to think about that. Oh my God, is it 3:15? Oh my God, we're gonna have to stop. I apologize. I didn't realize it was that. Well, okay, so we'll finish this next week.
I mean, tomorrow?
We cannot do it tomorrow, and I'll explain why in a second. So what's happening here? This looks like it's going to infinity. if I look at this. So we need to think about why something doesn't seem to be working here. We'll talk about that on Tuesday. Does anybody have a question about what's on the board before I stop the recording, and we'll talk about some other stuff? Anything? All right, great. So we'll finish this on Tuesday, at least discussing this, and we'll do more examples. We're going to give you some homework and all that fun stuff. So I'm going to stop recording now.